Hello? So, good afternoon. Welcome to this edition of the NITheCS Colloquium. I'm Francesco Petruccione. I'm the director of NITheCS. And today I have the really great pleasure of introducing Dr. Ryan Sweke to you because we go back a long time. Ryan was my master's and PhD student back in the UK's 10 days of my career. Yeah. After his PhD, in 2017 or something like that. He went to Berlin as a postdoc with another ex-student of mine, Jens Eisert. Yeah. From there, he moved to the US, yeah, in IBM Quantum Research something labs in San Jose. And since January, he's back at Ames. Yeah, you can see his branded T-shirt. Yeah, so we are very happy to have him back in Cape Town and surroundings. So welcome back, Ryan. Yeah, and because it's the International Year of Quantum Science and Technology, we asked Ryan to give us a nice talk on quantum computing. Yeah, so Ryan, welcome back, and we're very keen to listen to your talk. Thank you.
Thank you so much, Francesco, for the introduction. And yeah, I'm very, very happy to be back here and given this opportunity to talk a little bit about the work that I've been doing and the work that I would like to do and the work that everybody here has an opportunity to be a part of in the next few years. So yeah, like Francesco said, I'm currently at Ames, the African Institute for Mathematical Sciences, and this is kind of the view of the front door of our campus. And if you take a few steps back, that's what it's looks like. It's in Muizenberg. So if anyone is interested, I highly encourage you to come visit, and you'll be welcomed with open arms. Okay, so the title of my talk is Quantum Computing, Challenges and Opportunities. And I really hope that I can give you a very zoomed out kind of bird's eye view of the field of quantum computing as it is at the moment. Kind of my goal would be that you could walk out of here with the ability to sort of fact checked press releases that you see, or when you see something in the news and you don't know whether it's hype or reality, that you maybe get some kind of mental checklist that you can say, oh, that doesn't really feel quite right, or oh, that's actually real exciting progress. Okay, so of course, in order to give you an overview of quantum computing, I should tell you what a quantum computer is. But unfortunately, before I can tell you what a quantum computer is, I need to tell you what a classical computer is. So kind of a classical computer is what quantum computing people call a regular computer. So kind of in this talk, when I say classical computer, I mean your laptop. So I'm going to give you a kind of mathematician's perspective of what a computer is, and then we'll try connect it a little bit with the actual devices we have on our desks, and this will give us a foundation to understand hopefully what a quantum computer is. So from my perspective, at a fundamental level, a classical computer is four things. The first thing it is a collection of bits. So what is a bit? Okay, so we have some collection, we have n of them. And now a bit is just some object that can be either 0 or 1. So you can think of this as being either on or off. And a computer is made of a collection of bits, things that can be on or off. And it's going to be convenient for us to kind of introduce a little graphical notation like this. And you can kind of think of 0 as being an arrow pointing straight up and 1 being an arrow pointing straight down. So a computer, the first thing it is it's a collection of bits. But now you need to compute. You need to kind of do transformations. But before you do that, the first thing you have to be able to do, okay, so the state of the computer is a bit string. This is just some list of zeros and ones. And the next thing you need to be able to do is you need to be able to kind of prepare these bits in some fixed initial state. Every computation, it starts from some sort of reference state. Let's say all the bits have to be in the state 0. And once you know what the state of all the bits is, then you can start to do a computation. You kind of encode the input that you want to do some computation on. But it's important that you can put your computer into a state where you know what it is. When you turn it on, you know all the bits, they're in 0. Okay, and now the important part, you need to be able to do a computation. So if a computer is a list of bits, then a computation is a transformation of these bits. And kind of if you start with some bit string and you end with some bit string, then a computation is a function from bit strings to bit strings. And ideally, you want to be able to implement any function. Like a computer is only useful to you if it can really implement any transformation of bits. Okay, so this is our computation. Our computation is some function from the input bits to the output bits. And what a computer programmer does is they design this function. So maybe you do it in Python, maybe you do it in C++, but fundamentally what you're doing is you're designing a transformation that takes some set of bits to some other set of bits. Okay, and so now if you've done things right, the solution to the problem you're trying to solve should be encoded in these bits, the output bits of the computation. And so what you need is you need the ability to read those bits. You need the ability to see which ones are 0 and which ones are 1. So you need to be able to extract the information. And yeah, like I said, this information, like if you've done everything right, will encode the solution to your problem. So essentially, at least the perspective I want to give you, or that I want to encourage, is that you should think of a computer as a device which manipulates bits, and really to be universal, to be applicable.
Just give it a second. It will take 2 minutes, and then the power will be back on. The generator will automatically kick in.
Of transformations that you can prove that if you can implement the small set of transformations, then by combining them you can actually implement any transformation. So basically, like the way you specify this function is by writing down like a circuit that consists of these simple operations that combine bits. So this is an AND gate. If you put 2 zeros in, then you get a 1 out. That's a NOT gate. It takes a 1 to a 0. The point is that those are simple, and if you're trying to build a computer, you can just focus on being able to realize those, and if you can do them, then, well, in principle, if you put them together, you can realize any computation you want. And what a programmer does is they figure out the circuit that implements the transformation they want. Okay, so now this is kind of a mathematical definition in some sense. A computer is a set of bits on which you can implement any arbitrary Boolean function. But to build a computer, you need to find some physical system which can realize a bit. At the end of the day, you're going to need some actual physical system that can be in either the state 0 or the state 1. And then you can start to think, how can I manipulate that system in such a way that it realizes gates? And luckily for us, we've known since, I guess, around the 60s that a transistor is a fantastic way to realize a bit. This is basically a little electronic switch. And once you know that you have this physical system that can realize a collection of bits, well, then you can run with it and you can build a computer. So that's kind of my applied mathematician's take on what a computer is. But now it's great because we can start to think about what a quantum computer is. So fundamentally, a quantum computer, and we're going to do this by analogy, instead of being a collection of bits, it's going to be a collection of things that we're going to call qubits or quantum bits. And for now, I'm just going to illustrate them with this symbol here, psi. Quantum people love using psi to represent the state of things. Okay, so I have to tell you what a qubit is. And okay, so you have a collection of them. This is your analogy of the kind of fundamental thing in which you encode your information. And for those that have some linear algebra background, a qubit, all it is it's a unit vector in a two-dimensional complex space. So you have C2, and you know that there's a basis 0 and a basis 1. And now the qubit is just some state that's a linear superposition of 0 and 1, and it has to be normalized. Okay, so if you know some linear algebra, that's a definition that makes sense to you. A qubit is just a unit vector in the complex plane. But if you want a kind of more graphical idea or intuition of what that is, you can think of a qubit as being something whose state is described by an arrow that points somewhere on the surface of a sphere. So now here you can also get a good sense of how this generalizes a classical bit. Because remember, a classical bit was an arrow that either pointed straight up or straight down. And now a qubit basically can realize all the things that a classical bit could. It can point straight up or it can point straight down, but it can also point anywhere on the surface of the sphere. So a qubit has some sort of like continuous degree of freedom that it can realize. Okay, great. So now we know kind of what the fundamental unit of a quantum computer is. It's a qubit or a quantum bit, and a quantum bit generalizes a classical bit the way that I've illustrated here. Okay, and then just like in a classical computer, in order to be able to do something, we should be able to put our computer into some sort of fixed initial state. So basically, we should be able to initialize all our qubits into the zero state. And then again, just like in a classical computer, we want to manipulate the qubits now. The computation is some transformation of the state of the qubits. So we want to be able to implement an arbitrary transformation of the qubits, but because the qubits have to be normalized, the transformation that takes a kind of set of normalized qubits to another state, which is guaranteed to be normalized, is a unitary operation. So again, for those of you that done linear algebra, you'll know that unitaries, they preserve inner products and norms. So kind of that's the thing we want. You start with a normalized state, you're guaranteed to end up with a normalized state if your operation is unitary. Okay, so here the computation is a unitary. Okay, now you should be able to tell me what the next thing is. You have to be able to read out the information. You've done some transformation of your qubits. You want to get the information out at the end. So the final thing is the ability to make qubit-specific measurements. You should be able to look at them and see what's in them. Okay, and we represent a measurement of a qubit with this little dial, which represents a measurement device. I really actually love this notation that quantum computing people have come up with for a measurement. But now kind of the trick comes in, or the thing that's very different about quantum computers is that when you measure a classical computer, you do some computation and you look, you see this bit is in 0, this bit is in 1, that bit's in 1, and you know that that's what it's in. On a quantum computer, when you measure it, you will see some bit string. The thing is, if you redid the computation and you measured again, you would see a different bit string. And if you redid the computation again and measured again, you would see a different bit string. And if you did it again, you would see a different bit string. And so basically what's happening is when you measure the output state of a quantum computer, what you're doing is you're sampling from some probability distribution over bits. So again, this is very different. When a computer does a program, it arrives in a fixed solution. But when you measure a quantum computer, you get a sample from some probability distribution, which is defined by whatever output state you have after your computation. And so now you might think, okay, but how on earth can I use this to solve a problem? Because I need the solution. If I'm looking at it and it's different every time, how am I going to extract the kind of what the answer is? So basically, the computation is defined by the unitary, and you want to design the unitary, you want to design the program in such a way that the probability distribution that's defined by the output state is peaked on the bit string that encodes the solution. So you will get a different bit string every time you measure it, but if you've done your job right as a quantum computer programmer, then it should be the case that most of the times when you measure, for instance, this one that has the highest probability, is the bit string that encodes the solution to the problem that you want. So kind of this is the fundamental idea of what's going on in a quantum computer, and yeah, now we can explore a little bit whether this helps us. And maybe just before going on, I should mention that just like in the classical case, it seems very hard to implement an arbitrary unitary operation, but it turns out that there's a universal gate set, single qubit gates and C0s, and again, you're lucky in the sense that if you're an experimentalist in your lab, you only have to go and focus on how to realize these, and then in principle, you can put them together and do any unitary operation. Okay, great. Wait, what's happening here? Oh, there we go, sorry. So, I've gone too far back. Give me a second. Finding my place. Okay, so we've seen a quantum computer is a collection of stable qubits with the ability to prefer a fixed initial state and the ability to implement an arbitrary unitary operation and the ability to make qubit-specific measurements. But again, this is a mathematical definition. You know, like I've defined these qubits as linear algebraic objects, the transformations are unitaries. Again, the key point is that if you want to build a quantum computer, well, then you need some physical system which can realize a qubit. just like a transistor is a very natural and convenient switch, we need some physical system that is naturally described by a qubit. But we're very lucky in that nature gives us many such systems. And in particular, any two-level quantum system will be described, or a qubit is the correct way to describe any two-level quantum system. So I think that maybe I can just elaborate on what I mean by a two-level quantum system. So quantum mechanics is the theory that allows us to describe and make predictions about the atomic world, atoms, electrons, and molecules. And for many of those systems, for instance, if you take an electron, it turns out that in order to describe them correctly, in order to make predictions about their behavior, you have to assume that they have two states. For instance, an electron, you say it's either spinning up or spinning down. And quantum mechanics, or the rules of quantum mechanics, will tell us that, well, the spin state of an electron is precisely described by some unit vector on this sphere. And so basically we see that just like transistors realize bits, they realize switches, two-level quantum systems like electrons, they realize qubits. Like you describe them exactly like this. Okay, so that sounds great. They're everywhere, and let's build computers out of them. Unfortunately, the issue is that we also need to control these physical systems. So we not only need to have them, we need to be able to initialize them into a state that we know what it is. And then once it's initialized, we need to be able to apply these gates. And this is extremely hard because quantum mechanical systems, they don't like to be interacted with. When you interact with them, like we've seen, they collapse into some system probabilistically. And so somehow if you want to build a quantum computer, you have to interact with these systems, you have to apply these gates without causing them to collapse. And this is extremely challenging. But luckily we have some candidate systems that we think we can do this with. So the first one is trapped ions, and this is when you take some element and you kick an electron out. And so now kind of there's this two-level system of the atom with the electron and without the electron, the ion. You can trap it in a magnetic field and you can show that it's a qubit. And actually in 2012, the Nobel Prize in Physics went to Serge Haroche and David Wineland for kind of years and years and years of work that they put into learning how to manipulate these qubits, how to put them into like a specific configuration, how to do very simple gates on them. Another thing that's very kind of popular, or that a lot of effort has gone into at the moment, is superconducting circuits. It turns out if you cool down a very specific type of superconducting circuit element to absolute zero, then again it behaves like a qubit, and you can manipulate it to do gates. Or finally, you could use photons. Photons are somehow one of the most representative quantum objects you can think about. And in 2022, actually, the Nobel Prize in Physics was awarded to a group of people for again years and years of work of figuring out how to manipulate these qubits made out of photons, how to kind of initialize them and process with them. And so basically, there was a Nobel Prize in physics for quantum computing in 2012 and one in 2022. So if the pattern continues, then we should get one in 2032. So kind of everyone in this room still has a good chance of doing the work that can get you a Nobel Prize. Okay. So the important point that is that we really don't have a transistor yet. Now all computers are kind of made out of the same thing, transistors. But current quantum computers, there's kind of a competition between all these different ways to realize a qubit, and there really hasn't been a sort of transistor moment yet. We don't have a standard. We haven't kind of converged on USB yet. Okay, so I've told you what a quantum computer is, but the very first thing that you should ask me is like, why should I care? Okay, you can define this notion of a quantum computer, but like, why should I be interested in it? And the first thing that so the colloquial answer is that you should be interested in quantum computers because they can solve problems that normal computers can't. But in order to kind of give you a real sense of what this means, I would like to tell you what it even means to say you can solve a problem with a computer, because I think this is not actually such an intuitive notion. So let's do an example. Let's imagine the problem of factoring a number. So you're given some number m, and you're promised that it's the product of two prime numbers, p and q. And now given m, you just want to output p and q. So let's say I give you 21, then it's 7 times 3. You should tell me 7 times 3. Okay, so remember that the input to our computation is in bits. So if we want to try solve this problem with a computer, the first thing that we have to do is we have to represent our input as bits. So those of you who understand the binary representation, this is the binary representation of 21. Okay, so that's what goes into our computer. 21 represented as bits. Now we need to design some circuit. Remember, that's what defines a classical computation. And what we want to do is design the circuit in such a way that the output bits encode the factors. And well, here we did it correct, and you can see that 111 is the binary encoding of 7, 11 is the binary encoding of 3. So our computation was right. We programmed everything correctly, and things were good. But now a crucial notion is this notion of the circuit depth, because what we care about is not whether we can get the right answer, but how long it takes us to get that answer. And so we need to formalize what it means, like what it is. We need to formalize the notion of the length of a computer program. And we're going to formalize the length as the number of layers of gates that you need to apply. And this kind of makes sense because you can imagine that each layer of gates takes, for instance, 1 second or 1 microsecond. And so the number of layers that you have, the circuit depth, is a good notion for kind of how long the computation takes. Okay, so we're going to think about the circuit depth as being some formal way to describe the runtime of the algorithm. Okay, and now here's the real key important thing. For any number that you want to put in, the representation in bits will be a certain size. So to represent 21, we need 5 bits. And so this circuit works. And this circuit should work for any number that has 5, that can be represented using 5 bits in binary. But if we want to factor another number, I don't know, like 86, we're going to need maybe 7 bits in binary. And so we're going to need a different circuit. And now we say that we have an efficient algorithm to solve the problem if it can generate for us circuits whose depth, in other words, whose runtime, always scales polynomially with the size of the input. Okay, so this is a total mouthful, but let's do an illustration. So basically what we can do is we can plot a graph like this, where on the bottom we have the size of the input, the number of bits that specifies the input to the problem we're trying to solve. And then on the y-axis, we can put the circuit depth, the depth of the circuit that we need to solve the problem, the amount of time it takes to solve the problem with the circuit. And basically what we want is that this curve grows slowly, that it can be described by a polynomial. Because what that means is if you can solve the problem when you have 6 input bits, you can also solve it when you have 8 input bits. And to kind of contradict it, the like opposite of that scenario is when the curve grows exponentially. Because then maybe you can solve it for 2 bits and 4 bits as inputs, but you definitely can't solve it for 8. And so basically the idea is we say we can solve a problem if we're reasonably confident that we can solve bigger and bigger and bigger instances of that problem without running into some kind of catastrophe at some point. Okay, so basically we consider a set of circuits to be efficient if the time scales reasonably with the problem size. Okay, so now I think I can tell you finally why quantum computers are interesting. Because now that we have like a very precise mathematical notion of what it means to be able to solve a problem, we can categorize problems into those problems that can be solved efficiently and those problems that can't be solved efficiently. And we can create one set for all the problems that can be solved efficiently with a classical computer and one set for all the problems that can be solved efficiently with a quantum computer. So let's do that. Mathematicians have defined this class P, which stands for polynomial time, all of those problems that you can solve in a polynomial amount of time. And then there's another famous class of problems called NP, and those are the problems that you can check that solutions are correct, even if you can't find out about it. And maybe some of you have heard about the problem of P equals NP, trying to understand whether these are the two same classes, and that's a big open problem. But now we can also draw, okay, so there's NP complete problems, we won't worry about those. And now you can also draw this set, which is BQP. So those are the set of problems that you can solve efficiently with a quantum computer. The BQP stands for bounded quantum polynomial time. Okay, now my claim is that you should only care about quantum computers if there's some problem which is not in P, but which is in BQP. Basically, a quantum computer is only interesting if there's some problem that you can't solve with a regular computer that you could solve efficiently with a classical computer. I mean, it could be that the set BQP is completely inside of P, that every problem you can solve with a regular computer, you can solve with a quantum computer, and then there's just really no point in even starting to be interested in them. But luckily, in the mid-90s, someone called Peter Shaw came up with a quantum algorithm for factoring numbers. And factoring numbers is a problem which currently sits outside of P. We don't know of any good, efficient classical algorithm to do this. And kind of, maybe fortunately for the field of quantum computing, people care a lot about algorithms for factoring numbers, because the whole of modern cryptography rests on the assumption that this is hard. Every time you do some sort of internet transaction, your credit card details are kept safe because in order to get your credit card details, someone has to factor a big number. And at the moment, that's hard with regular computers. So when Peter Shaw showed that, okay, you could, if you had a quantum computer, you could factorize numbers, then people all of a sudden thought, let's build these. Like this is something that's worth building. So basically the crux is there exist problems which we can solve efficiently with a quantum computer, but no efficient algorithm is known for classical computers. And the real question we're interested in here is like, okay, we know this is worth looking at. There's something interesting going on here. But is this it, or are there more? And this is the question that we'll explore in the rest of this talk. But I should also point out that we learn a lot of extremely fundamental things by thinking about quantum computing. Thinking about quantum computing, formalizing quantum computing, trying to understand what quantum computing is, has made us realize a lot of things about quantum mechanics itself, and in turn, kind of the fundamental nature of our universe and of physics itself. So even if we were to never build a quantum computer, I would still say that the whole effort to build a quantum computer has been totally worth it for the things that we've learned about the world we live in. And also, if you try to build a quantum computer, then you also learn a lot about how to manipulate kind of quantum states of matter. Okay, so quantum computers sound great. Where are they? This is kind of the next question. We know that they can do these interesting things. Why don't we have them? And the answer is we do have them. In 1985, quantum computers were really just drawings. They were purely theoretical objects that people had thought of. And now they are real quantum computers. So this is at IBM, and this is someone working on an actual quantum computer that has more or less 100 qubits. This is a superconducting quantum computer. So this kind of chandelier-looking thing is actually an extremely fancy fridge. And then the actual chip is just kind of this tiny chip that's in there. But these are real. And I mean, there's many of these. And incredibly, okay, so there's just a wild amount of investment in quantum computing at the moment from all the big companies that you could expect and governments. And the incredible thing is that you can use these quantum computers. So for instance, if you go onto the IBM webpage, you can create an account and you can actually go and run computations on an IBM quantum computer. So it's kind of an unprecedented thing that is happening at the moment in the sense that all of us have the ability to go and to manipulate these fundamental states of matter via the cloud. It's really, it's an unbelievable chance to do experiments that for many, many years could only be done in labs with hundreds of people working in them. Okay, so we have quantum computers. And then the next thing you should ask me is, are my credit card details safe? Because now I've kind of told you, like, if you had a quantum computer, you could break cryptography using Shor's algorithm. And then I told you we had quantum computers, but our kind of world order seems stable. It seems like cryptography is still working. So something is wrong. And the thing that's wrong is that noise is a major obstacle. So now I kind of have to describe to you what noise is. And basically, let's say you want to run this quantum circuit. Let's say that's Shor's algorithm. That's the circuit that spits out the factors of a number. Unfortunately, because it's very hard to do these gates, and because it's very hard to build these qubits, every time you do a gate, something slightly unwanted also happens. And these kind of like unwanted things that we don't have control over, that we just can't get rid of in our best attempts to build qubits and do gates, that's what I call noise. And unfortunately, like, nowadays, if you don't do anything about it, this noise just accumulates, and at the end you get something which is just not even close to the right solution. Okay, but we've known all along that noise was going to be an issue, and people have been working on this again since the 90s, and we have a solution, and that solution is fault-tolerant quantum computing. And the idea of fault-tolerant quantum computing is for every qubit that you're meant to have, you triple them or you quadruple them, and then basically you find a way to use these other qubits to correct the errors that happened on that qubit. So you try to do a gate, some errors happen, but then you do some measurements of these qubits, you feed them into some classical computer, that classical computer figures out what went wrong, and then you do some other like action on your qubits, and then in the end you know, okay, we've corrected the errors and things are great. And you can do this, and then in the end you will get the right answer. And this is an extremely active field at the moment with a lot of development, but it's very much in the future because at the moment, kind of the best guesses for how many qubits we need to realize one qubit is something like 200. And so the overheads in doing fault-tolerant quantum computing are truly gigantic. They're prohibitive at the moment. So basically, people then said, okay, this is the future, but what could we do now? And what we can do now is what people call noisy intermediate scale quantum computing. So we have noisy quantum computers that are of an intermediate scale. They have 100 qubits. And that's kind of now. And the idea or the question now is like, I've got what I've got. It's limited depth, it's got noise, but what can I do with it? And this is, great, time's good. Exactly, so you can kind of see these two paths for quantum computing. There's where we want to be in the future, and this is under active development. How can we build better and better error correction codes? How can we push down the overhead you need? And then there's now, and I'm going to describe to you some research directions in the one and some in the other. Okay, so let's just say that all the experimentalists and theorists succeed, and they put a fault-tolerant quantum computer on our desk tomorrow. What would you do with it? So the very first thing you would do with it is you would break all the cryptography that exists, and you would learn everybody's secrets that have been cached over the last 50 years. But then kind of you would steal all the secrets and like what next? That would be the question. Surely there's something more you can do with this miraculous device that's manipulating fundamental states of matter. So we've seen that a quantum computer can factorize numbers efficiently, but like really is that it? Because maybe it would be a bit disappointing if all of this effort was just going into breaking cryptography. So actually, Richard Feynman, who was maybe the first person to kind of articulate the idea of a quantum computer in the early 80s, his idea was really like, maybe we can build quantum computers to simulate quantum mechanical systems themselves. So I'm going to explain what this means, but he has this nice quote, which is kind of just an obligatory quote that you have to put if you give a talk on quantum computing, which says that nature isn't classical, and if you want to make a simulation of nature, you better make it quantum mechanical. Okay, so let's try and understand what this means. So what is a quantum mechanical system, and what does it mean to simulate it? So a quantum mechanical system is some system which is a collection of qubits. So for instance, this might be some mathematical model of some two-dimensional material, like a sheet of some substance, like graphene, for example. And we know that we can model each of kind of the constituent particles of that sheet of the material with a qubit. This is like a good mathematical model of that material. But now very often when you want to develop a material, for instance, let's say you want to develop a superconductor, what you really want to know is what happens if I just let this material sit. Like these qubits are going to evolve because they interact with each other, and that causes them to transform. And like if you want to prove that, well, this material is a good superconductor, you really need to know that the way that these qubits evolve is like a specific way. So we can call this initial state of the system psi 0, and we know it evolves in time. And basically, those who've studied quantum mechanics here will know that the final state, the state that's at psi t, it has this mathematical description. But the point is that even though we can write down the expression for what that state is, it's very difficult to calculate. And if we want to kind of test properties of this material, we need to be able to know properties of that state. And the idea is, could you use a computer to calculate what that step is, to evaluate this formula, basically? And this problem of evolving a quantum system in time, it's called Hamiltonian simulation, because this object H, which is the thing that describes all the interactions between these particles, is called the Hamiltonian. And this is kind of some very fundamental problem that occurs in materials development, in drug development, in quantum chemistry. And this is hard for a regular computer. But we already think that this could be easy for a quantum computer, because after all, I mean, our quantum computer is a set of states, and we know that these evolve unitarily, and that's the unitary here that it evolves by. So if we can just program our quantum computer to realize that unitary, well, then we're going to have that state, psi of t, in our quantum computer. So this really is kind of the most natural application of a quantum computer. Nature consists of qubits, and nature is qubits evolving. And so can we use our quantum computer to kind of simulate the natural evolution of qubits that is happening in nature? And like I said, so this is really crucial for the design and development of novel materials, for molecular dynamics and drug design, and for many, many, many other problems. And importantly, this seems to be hard for classical computers. So a lot of current effort on major supercomputers goes into trying to solve this problem with brute force methods. Okay, and the question is, can we do it efficiently with quantum computers? Okay, so I've given you one answer of what we would like to do with a fault-tolerant quantum computer, but maybe we could be more ambitious. Like, is there more that we could do? And again, the answer is yes, because what we're looking for are quantum mechanical problems. We have this idea that quantum computers should be good at problems that kind of involve quantum mechanics. Like when you have to simulate quantum mechanics, maybe a quantum computer can be good. And there are many other naturally quantum mechanical problems. So one is, again, you just imagine you have some quantum mechanical system, some material, some like sheet of qubits. But now you ask, what happens if I cool this down to absolute zero? Because we know that all the really interesting quantum mechanical effects, they happen at absolute zero. Like if you want to build a Bose-Einstein condensate, you have to cool some system down to the absolute zero. And kind of again, mathematically, we know what the state will be. It's the state with the minimum energy. So this is the expression for the energy of a quantum state psi. And if you cool a system down to absolute zero, you're going to arrive in the state psi star, which minimizes the energy. And again, we have this mathematical kind of representation, but we can't calculate it. And so again, you could ask, can I do this ground state? This is called the ground state identification problem using a quantum computer. And it seems like maybe you could, because it involves quantum mechanical systems. Another thing you could do is you could take a quantum mechanical system and you could say, okay, well, you can never completely isolate quantum mechanical systems, actually. They always interact with their environment. If you have some sort of lab, then there's kind of a light coming in. It's interacting with an environment. And when quantum systems interact with an environment, if you let them go on for a long time, they eventually thermalize, or they go to the state that we call a thermal state. And again, this is understanding properties of these states is very helpful if we want to understand and develop new materials that exist at room temperature or something like this. And again, we have this expression, but we can't explicitly calculate it. And so this kind of thermal state preparation or open quantum system simulation is a very natural problem. And again, both of these seem to be hard for classical computers, and there's the hope that we could do it with quantum computers, because again, there's many applications. Okay, so this is cool. We think, okay, there's this one problem we definitely can get an advantage for with quantum computers, factoring numbers. And then there seems to be all these other problems that are kind of quantum mechanical and that are useful if we want to develop materials or drugs or something like this. And that's a lot of motivation to build a quantum computer. And if you can solve those problems with quantum computers, you will have a huge impact in the world. But there's many, 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 many more non-quantum problems that have nothing to do with quantum mechanics, that also take tremendous quantum computing resources to solve. So, for example, solving systems of equations, solving linear, partial, or stochastic differential equations. These problems are sort of the bread and butter of scientific computing. So if you study applied mathematics or mathematics and you take a course in numerical analysis, you go learn algorithms for doing this, for solving systems of equations, for solving partial, linear, stochastic differential equations. And if you could do these with a quantum computer, then the applications would be endless. You wouldn't be able to list them. And then there's also things like optimization problems in machine learning. And I think I don't even need to convince you that if you could get an advantage for something like machine learning, which is revolutionizing our world, well, then you would have a huge, huge impact. So again, you could ask, could we use a fault-tolerant quantum computer for these? And so the question now is, that's what you would like to do with a quantum computer. And kind of my job here is to tell you, what can I actually do with the quantum computer? Today, in this day and age, like, what is possible? This is kind of the future, the vista, the things that we would like to achieve. And what can I actually do now? So we can summarize the state of affairs like this. And this scheme that I'm going to show is thanks to someone called Lin from UC Berkeley. And I really liked it, so I'm going to borrow it from him. So essentially, you can kind of make a plot. And on the bottom, you can have the range of applications. So this is kind of the number of things that you could do if you could solve a problem. And on the y-axis, you can put the existing evidence of quantum advantage. So like how confident we are that you can get a kind of advantage by using a quantum computer. And the current state of affairs is something like this. At the very top, you have cryptography. So we know that by running Shor's algorithm, we can solve cryptographic problems. And this, it surely has scientific and industrial applications, but they're relatively narrow. Then after that, kind of come the quantum mechanical problems that involve implementing a unitary, like simulating the time dynamics of a system. And here we've got like slightly less evidence that you can get an advantage with quantum computers, but certainly the range of applications is larger. And this is for Hamiltonian simulation. And then, like I told you, there's these other problems which are quantum mechanical, but where it's not quite unitary evolution, where it's something a little bit trickier. There's so-called non-unitary quantum problems. And this is things like finding the ground state of a system, preparing thermal states, simulating open quantum system dynamics. And this would have even more applications, but at the moment there's even less evidence for speedups. And finally, there's the fully classical problems like linear systems, ODEs, PDEs, SDEs, optimization, machine learning. And kind of, I really think that this is a great way to summarize the kind of existing state of affairs in quantum computing. And so if someone tells you, oh, I have a quantum algorithm for machine learning, you should be skeptical. Because we know that quantum computers, what they're good at is manipulating quantum mechanical systems. And we would love to have algorithms for fully classical problems, but the honest truth is that at the moment we're not quite there. Kind of, this is the roadmap. Okay, and I should say that for fully classical problems, one of the difficulties is that quantum computers start with quantum states and they end with quantum states. And so for problems that naturally start with the quantum state and end with the quantum state, it's great. But for an SDE or machine learning problem, you're given pictures of cats and dogs. How are you going to put this into your quantum computer? It's not so easy. There's a lot of work that has to be done there. Okay, so what can we do now? So we know there are some problems that we can get a quantum advantage for. These are the ones that I showed you on the previous slide. But remember, all of that was if we had a fault-tolerant quantum computer. That was in the world where we just assumed that all the experts had succeeded and we had really good quantum error correction. But we live in the world, so factoring is an example of a problem where we know we can get a quantum advantage. Hamiltonian simulation is another. But remember, we live in a world where we only have these NISQ computers, these noisy intermediate scale quantum computers. And so you can think of the class of problems that have a quantum advantage, the class of problems you can solve with a NISQ computer, and the question is there anything there? That's is there anything you can do with a quantum computer at the moment that's interesting? And well, since a few years, the answer is yes, there is a problem. And when people solved that problem, they got straight onto the cover of Nature. And it was people at Google that finally managed to solve this problem, or they claim to solve this problem that can't be done by a classical computer, but can luckily be done by the quantum computers we have now. So this sounds interesting, and like I told you, what I would really like you to be able to do is kind of get some sort of understanding when you see a news article, when someone says, oh, quantum supremacy or NISQ or quantum advantage, which are the kind of words that you see when people write newspaper articles about quantum computing. What do they mean? So let me explain to you what the problem is that they solved in this paper. Okay, and I should say that when people finally demonstrated that quantum computers could solve a problem that classical computers couldn't, they said that we had obtained quantum supremacy, but this term feels a little bit extreme for my liking, and so we'll just refer to it as quantum advantage. So what was the problem that they solved using a quantum computer and was in this intersection? Okay, so the problem they solved is something called random circuit sampling. And random circuit sampling is the following problem. You're given a description of a randomly drawn quantum circuit. So imagine this is the set of all quantum circuits that have a specific depth, f of n. And now what you do is you draw a circuit randomly from that set. Okay, so there's technicalities. How do you draw a random quantum circuit? Just imagine you could solve it. And now I give you a description of the circuit that I drew. So I say, first you do this single qubit gate, then you do a C0. I write down on a piece of paper for you. I describe the circuit to you, or I give you this drawing. And now you know that if you were to run that quantum circuit and measure it, then you would get a sample from a probability distribution. And the goal of the problem of random circuit sampling is to sample from the distribution defined by the quantum circuit that you drew randomly. So this is the problem. I give you a description of a quantum circuit, and you have to give me back bit strings sampled from the same distribution that you would have sampled from if you actually ran this computation. Okay. And now the first thing that you should see is that this looks super easy for NISQ devices. Because if I give you a description of a quantum circuit and ask you to sample from this distribution, and you have a quantum computer, well, then all you do is you run that quantum circuit and you measure it. It couldn't be easier. Literally, the problem is run the quantum computer. But it turns out, after lots and lots and lots of incredibly hard work, that this problem of simulating randomly drawn quantum circuits is actually hard for classical computers. But really, the key point is that it has to be randomly drawn. It means kind of like, on average, random quantum circuits are hard to simulate. Okay, and this has some assumptions because it's a technical thing that took many years, but they're all reasonable. Okay, so this is the problem that Google showed they could solve with their quantum computer, and that many theorists proved that you couldn't do with the classical computer, and that got onto the front cover of Nature. This is kind of like what I told you now is I fully explained kind of the big news in quantum computing in, I think it was 2022 or something like this. Okay, but there's two problems here. Or like if you're critical or maybe you're a referee for Nature, this is what you should have said to them. The first thing is that we have this kind of like pyramid of where we can say the evidence for quantum advantage and the range of scientific and industrial applications. And unfortunately, random circuit sampling sits like right at the top there. It's just a little dot. Basically, the only application of random circuit sampling is demonstrating that quantum computers can obtain advantages. This problem was literally manufactured from thin air purely to be a problem that quantum computers could solve, but that classical computers can't. It really has no advantages. It's like a delta function that's sitting there. And but like despite being skeptical, I have to say that being able to actually do this gives us amazing evidence that we're making progress. Like we can at least simulate quantum computers with a quantum computer, which is kind of a first check mark that you would like to do. The second problem is that, okay, so there's a set of problems that we have an advantage for and a set of problems that can be done on a NISC device. But ideally, you would also like the solution to the problem to be verifiable. In other words, if I tell you this is a solution to the problem, you should be able to easily check that this is a solution. And incredibly, for the problem of random circuit sampling, we don't actually know how to check whether some samples were actually a solution to the problem. Because imagine this, you're a referee, and Google's on one side, and I'm on the other side, and now Google wants to prove to you that it can solve random circuit sampling, so they give you the samples that they claim they got from their quantum computer, and I give you the samples that I got from some like classical simulation I've done. We can prove that you as the referee cannot determine whether Google actually won the game or not. It's kind of a ridiculous situation where like, if they did everything right, then yes, they did solve the problem, but they can't prove to us they solved the problem. And so you can kind of never convince a skeptic that actually we have realized the quantum computation. Okay, so the advantage is not verifiable. But this gives us another tool to understand the current landscape of quantum computing, in the sense that, okay, now I'm stealing a schema from Scott Aronson. I'm lucky to have these people that have kind of thought about how to conceptualize the current landscape before me. But essentially, kind of, you can think of there being these three sets. There's the problems which you can get an advantage for a quantum computer, but some of those you can't do with the quantum computers we have now. And then there's the set of problems that you can verify the solution. And we know that we should think about quantum advantage in terms of this pyramid. Ideally, we would like things lower down on the pyramid, like with a lot of range of scientific applications. And we know that there's some problems like factoring where we can easily check that the solution is correct because you can just multiply two numbers together and check that it equals the original number. And then there's quantum physics problems that we can solve and we can verify, but we can't do it now. And then there's random circuit sampling, which is great because we can do it, but it's not verifiable and it's kind of useless for anything other than demonstrating a quantum advantage. And so kind of what more is there? So very recently, some people showed that there's some physics problems that you can solve that are interesting with a quantum computer, but we're not quite sure whether you can get a quantum advantage for them or not. They're really on this border. We're not sure whether you can do those with classical computers, but nevertheless, it got on the cover of Nature. And they got on the cover of Nature by, okay, well, I'll explain it at the end. Okay, and then you might have heard a lot about quantum machine learning. Well, machine learning is revolutionizing society, and quantum computers are going to revolutionize everything. And so quantum machine learning is the next big thing. And there's thousands of articles written about quantum machine learning. But when you have this framework to kind of understand them, you see that, yes, you can use a quantum computer to do them, even one that we have now. And sometimes you can even verify the answer. But we don't know if you get a quantum advantage or not. The evidence for a quantum advantage is very low. And unfortunately, lots of quantum machine learning is not even verifiable. It's literally just something we're doing with a quantum computer without knowing that we get an advantage or being able to check we're even solving the problem. Okay, and the real question, the kind of, if you really want to do good research in quantum computing, you should ask yourself, can I design an algorithm that shows that there's some problem that's sitting here, that you can get an advantage with the quantum computer, you could do it now, and everybody can be convinced of the solution. And there's lots of people that are working hard on trying to identify a problem there. Okay, and so also, like I told you, like we have algorithms now which we can do with these noisy computers. That's why this article is called Cutting Through the Noise. And but people are arguing about whether they're advantageous over classical methods. And so basically the jargon that people say is that algorithms on this boundary can be said to offer quantum utility. And what that means is they're at least competitive with the best classical methods. We don't know if we can beat them, but there's some utility to trying the quantum method because it gives you an extra data point. Okay, so I'm getting towards the end of the talk, which is great because I think the time is running out. Perfect. So what are the challenges? Now we kind of have this great framework for understanding the landscape of quantum computing. And what are the challenges? Well, we can understand the challenges in terms of this diagram. So I would say the first kind of grand challenge, and this is a very zoomed out one, is can we provide evidence of quantum advantage for more problems? And again, we've seen K factoring, great. Unitary quantum problems, great. Non-unitary quantum problems, maybe. But if you really want quantum computing to have an impact in the world, then you have to show that there's quantum algorithms for kind of classical scientific computing problems. So basically, this is our current state of knowledge at the moment. And what we'd like to do is do work that allows us to kind of like push this triangle up. We would like to take these problems that have a lot of applications and show that we can give more evidence of quantum advantage for them. And you have to do this by developing algorithms, quantum algorithms that solve the problem. Okay, so what you want is good quantum algorithms for classical problems. And another way you can think about this is you want to take the set of problems that that we have a quantum advantage for, and you want to push it outwards. You want to expand it. That's a way that you can think of this type of research, because if you expand this, then you have a better chance of finding a problem in the intersection. Okay, and the second thing is that what we would love to do is we would like to take this set and make it bigger. So we know that there's a lot of problems we could solve if we had quantum computers, like good ones that were fault tolerant, but can we increase the set of problems that we can solve with these near noisy intermediate scale quantum devices? And to do this, so we want to expand this set outwards. And to do this, what you have to do is you have to develop error correction and error mitigation strategies. So like I told you, this is a huge and active branch of research. And I really, really believe that young people who want to make an impact in quantum computing, like, this is an amazing thing to work on. It's mathematical, it's interesting, it's active, people are doing experiments, and if you make a contribution there, you can halve the time it's going to take us to get a quantum computer. If someone comes up with an error correction code tomorrow that only needs 10 qubits to kind of correct the errors on a single one instead of 200, you've really, really, really drastically reduced the time until we have a quantum computer. Okay, and then there's lots more. Obviously, you could expand that set, or you could ask whether you can move a problem from there to there by giving a verification strategy. The thing I wanted to mainly introduce is this framework for thinking about it and for kind of challenging and receiving and understanding current research in quantum computing. And so kind of here, hopefully, is your official quantum computing critic checklist. This is the thing you look at next time you see an article in The Guardian or the front page of Nature about quantum computing. The first thing you ask is, how good is the evidence that this quantum algorithm gives an advantage over classical algorithms? Is there a mathematical proof? Is there just kind of some ad hoc plot against some classical methods? Or is there kind of like 30 years of experience that this problem is hard for classical computers? So factoring numbers is a great example. We have no proof that factoring numbers is hard for classical computers, but classical computer scientists have been trying for 60 years, actually since the beginning of algorithms, maybe you could say 2,000 years, to come up with good algorithms for factorizing numbers, and we still don't have one. So the evidence is pretty good. You have like 2,000 years of human effort. But yeah, a lot of people, especially for instance in quantum machine learning, there's no evidence that it's better than classical algorithms. Just, well, look at this algorithm I can run on a quantum computer. Okay, but how good is it compared to the classical one? Okay, and again, we've seen here that there's this kind of pyramid that you can use to evaluate this. And then you can ask, could this advantage be verified in practice? Like, if I run this algorithm, can I convince you that I've actually solved the problem? And this sounds strange that this should even be an issue, but it turns out it is. And then finally, you can ask, okay, well, there's an advantage and I can verify it, but is this something that we need to wait for a fault-tolerant quantum computer for, or is this something that we can do now? Okay, so those are the challenges. And now, like, I want to end on a sort of optimistic note with the opportunities. So addressing all these challenges really requires some sort of quantum-enabled generation of researchers. There's an extremely big set of very interesting problems that promise to have huge, huge impacts. But clearly, to work on this, you need to be somehow quantum-enabled. You need to understand quantum mechanics, quantum computing, classical computing. But luckily, learning quantum computing and interacting with quantum computers has really never been easier. So like I told you before, there's all these companies that are developing programming languages for quantum computers that are making their quantum computers available on the cloud. So for instance, Penny Lane is some company from Canada, Xanadu, Qiskit is IBM, Cirq is Google, and there's many more. These are kind of open source programming languages that you can use to run real quantum computations on real quantum computers. And they're open source and they have huge communities, Slack channels with 10,000 people that are willing to answer your questions. And I really think we have to take advantage of this opportunity. And unfortunately, at the moment, we're not. Oops. So I've put my animations in the wrong order, but it's fine. So there's a foundation called the Unitary Fund or the Unitary Foundation. And last year, they did a big survey of people asking them whether or not they use open source quantum software. And then you can see the percentage of the respondents where they come from. So the US is first. And basically, you have to go all the way down, I think, to like 23 or something before you see an African country, Ghana. Then you have to go to 25 and you see Nigeria, and then you see South Africa at 0.6% of people using open source quantum computing software. And really, what we should do is try to push this up. I think that I guess it's my job now to kind of make you excited about this and to tell you about these things and convince you that you should go there and you should try them. Because at the end of the day, there's lots of problems to be solved, and we have an incredible amount of talent here. And this is an opportunity that we should take and that I encourage you to take. And there are lots of initiatives that are trying to help you. So there's the Quantum Leap Africa, which is started by AIMS in Ghana. There's the South African Quantum Technology Initiative. There's the Open Quantum Institute, which is an international institution. There's the Unitary Foundation, which kind of has a library of open source quantum software and projects. This year is the International Year of Quantum Science and Technology, and there's events happening all throughout the year. And then there's things like the Qiskit Global Summer School. So this is a summer school that IBM puts on, and last year I think they had 5,000 people attending, and this year they're expecting 20,000 or something like this. So there's really an incredible amount of opportunities, and I think that I really encourage everyone to get involved if this is something that sounds interesting to you. All the kind of resources and opportunities you need are there. There's no barrier to entry anymore at all. So that's the end of the talk. Thank you very much. And I just want to say that this is my email address, and I'm here, and I have energy, and I have motivation. So if anything that you saw here kind of appeals to you, feel free to send me an email, and we can meet at Musenberg and go for a walk on the beach and talk about quantum computing.
Thank you very much, Ryan, for an excellent talk. I'm sure we have plenty of questions, and maybe we can start with questions from the audience here. Please. Sorry, I'll give you that.
Thank you very much for the very interesting presentation. Well, there was a statement that you mentioned that is quite interesting, which it triggered a question about, in general, how the research goes in quantum computing. You mentioned that the only application for our CES, random circuit sampling, is proving that we are making progress. So I would just like to understand how it starts, like in general, like a new idea in quantum computing, how it starts from the theoretical aspect until it goes to being applied. For example, like in other words, like why did Google invest all this until it proved it?
Yeah, it's a great question. So I think the question is kind of, I would say, like a social question, in the sense that I think one thing we have to remember is that science is done by communities of individuals. And I think that kind of the consensus of what is interesting, what is worth investing effort into, this emerges as a consensus amongst the community who meets at conferences, who exchange and read research papers. And I think that for the origin of random circuit sampling, there was some group of people that thought, they had the opinion, that maybe there's physical reasons why you're just not going to be able to build a quantum computer. Maybe you're just never going to be able to suppress noise. Cosmic rays are just always going to kill your qubits. And so another group of theorists thought, well, how could I convince those people? And they said, well, maybe we can come up with a problem, and it doesn't have to be useful for anything, except showing that, like, actually it's possible to do something like that you can't do with a classical computer. So that was kind of the genesis of that idea. And then over time, people had better and better proposals, and eventually kind of there was this great moment where there were good proposals, good theoretical evidence that this was hard for classical computers, and Google had the ability to do the experiment. But really, it's this kind of how we decide what to do next and focus is kind of unpredictable dynamics of the community that does science together. And also, to be honest, this is again why I feel so strongly that it's important that people from South Africa and Africa are doing science, that are influencing the direction that like the community takes and how the community decides what are important problems to solve.
At the top, Donovan, thank you.
Hello, thank you so much for the presentation. I want to ask, where does the recent breakthrough from Microsoft fit into this? I mean, does it have a quantum advantage or is it verifiable? And thank you.
Yeah, that's a great question, and I can explain it to you. So, on this slide, where is it? Yeah. So basically, I told you that. Okay, so these qubits are noisy, and so to correct the noise, what you have to do is for every one qubit that you want, you have to kind of have like 30 or 200. So what Microsoft showed is that they can build a very unique type of qubit that is extremely robust to noise. So they used a kind of like completely different physical system to realize the qubit that has the property that it's extremely unlikely that any error will occur when you're doing a gate. And so the amazing thing is that if you build a quantum computer out of these qubits, then you don't need all the like extra like hundreds and hundreds of qubits to do error correction. So that was the huge breakthrough that Microsoft made. They didn't run any algorithm, they didn't solve any problem. All they did was they claimed that they've got one new type of qubit, just one. So IBM, for instance, has hundreds and hundreds, and Microsoft has said, we only have one qubit. We can't do anything with it yet, but if we put them together, we're not going to need error correction because this qubit, we can prove because of the physics of the systems that we built it out of, is very robust to noise. So that's what happened in this latest press release.
There's another question there at the top. Here we go. And then there at the top in the corner. Thank
Thank you. On the same question, I realized that Microsoft used Majorana particles for that. Do you have any intuition? Is that what you're actually talking about in terms of error correction? Those are the particles they use to create the topological.
Exactly. So those who have done some physics know that there's these particles called fermions and particles called bosons, and these have different kind of statistics. When you swap the particles with each other, it turns out that like different things happen in different of these cases. And then there's a very exotic class of particles that physicists invented on paper called anions. And these have different statistics. When you swap them around each other, like different things happen. And it turns out that because of the way that these particles behave when you kind of interact them with each other, you can do gates that are very robust to noise because it doesn't actually matter the individual path that these qubits took. In the end of the day, it just matters kind of the overall shape that they made. This is kind of a very abstract explanation. But essentially, since I guess 30 years, people have realized if you could build these like very exotic particles, then you could do quantum computing. And these particles are these Majorana particles, which are anions. They're neither fermions nor bosons. And exactly, that's what Microsoft made. They claim to have been able to build a material that has anions in it, these Majorana particles. Yeah.
Thank you very much. The last question is about fault-tolerant quantum computing. The communication with the classical computing so that they reduce the error. Does it affect the runtime of the entire circuit?
Yeah, so this is a huge challenge in error correction, is that this communication to the classical computer, the computation on the classical computer and the communication back has to be shorter than the time it takes for errors to accumulate on the device. Like this has to happen extremely rapidly. And so kind of when people are doing quantum error correction experiments these days, they build FGPA or FPGA boards that like only run this very specific algorithm and sit right next to the quantum hardware. And I should say that one thing that people are very interested in these days is whether you can use machine learning algorithms to improve this process. Like, are there machine learning algorithms that can kind of get some information from the circuit and learn how to correct the errors using less time than the algorithms we've developed properly? But yeah, this is a huge bottleneck. There's a very strict speed limit here, and if you're under that speed limit, you're just not good enough. Yeah.
Donovan, there was a question. Okay. Yeah. You go ahead, and then we can.
Thank you for the presentation. My question is, how do you envision the integration of quantum computing with quantum classical computing system?
Yeah, that's a very, very, very good question. So I hope I've convinced you that quantum computers, they're not just fast computers. It's not like we're just going to throw away computers and then going to have fast computers. There's some very, very specific problems that maybe quantum computers will speed up. And so I think the future of computing is that you have high performance computing, which is doing the majority of hard work. And then for those very specific parts of the computation that are very hard, the solution will get outsourced to a quantum computer and sent back. And your question is very prescient in the sense that at the moment in the community, there's a big focus on the integration of classical high performance computing with quantum computing. How can we use the classical computer as much as possible so that we only have to use the quantum computer for these very specific things that it can give us an advantage for? So the answer to your question is that I can't envisage it. It's very much a work in progress, and there's lots of possibility there. Yeah.
Yeah, thank you very much indeed for such an excellent talk. So you gave us only one, I'm a pure mathematician, so my question will be from that angle. You gave us only one example of a mathematical problem where we have quantum advantage. Surely there are others. And what my question is, if I have some combinatorial, let's say some combinatorial problem that I know that on a normal computer it takes a bit of time to solve, maybe a few years. What are the chances that if I try to use the quantum computer, I will manage?
So I can give you a good intuition for this. So far it turns out that there are quite a few examples of classical mathematical problems that we know we can get a quantum advantage for. But so far all of these involve solving at some point what's called a hidden subgroup problem. There is a group, and solving the problem requires identifying some particular subgroup in this group. And if you can do the Fourier transform over this group, then you could solve the problem. And what quantum computers are doing is they're giving you a very efficient way to do the Fourier transform over groups. So this is the tool you have as a mathematician, Fourier transforms over groups. And so what Peter Shaw did that was amazing was that he reduced the problem of factoring to the problem of doing the discrete logarithm, which then helped him solve this kind of hidden subgroup problem that's hiding within factoring. Yeah.
So you're saying that all mathematical problems that potentially can be solved should be reduced first to this single.
So what I'm saying is using the techniques that we know at the moment. So if you have your favorite maths problem and you would like to know, well, could a quantum computer could solve this? The very first thing I would suggest you to do is see if there's a hidden subgroup problem hiding in there. If there's not, it doesn't mean that a quantum computer won't be able to do it. It just means you'll have to invent a genuinely new quantum algorithm to do it.
Thank you very much.
What is the quantum analog of logical connectives?
Of logical connectives? So you're talking about ands, ors, nots, and
yeah.
So
very basic logical gates.
Yeah, so it's a good question. So this thing here is called a controlled NOT gate. So basically what it does is if that's 0, then it does the identity on that bit. And if that's 1, then it does the NOT on that. So that's kind of the one fundamental 2-qubit operation. And then I need this slide of what is a quantum computer. So I had this picture of a qubit. So, classical bits, there's kind of only one thing you can do to it. You can keep it the same or you can flip it. So the kind of fundamental operations for quantum bits is rotations of this arrow on the sphere. So the fundamental single qubit operations are rotations around a certain axis. So there's a XYZ plane, and people talk about, oh, you do a pi/2 rotation around the x-axis, and then you do pi/3 rotation around the y-axis, and those are the kind of fundamental operations. Yeah.
Thank you. Any more questions? Here we go. Donovan, can you? We can ask a question from the online audience.
Good evening. For organizations or companies to become industry leaders in a quantum industry, which is the more important focus right now, quantum hardware or development of theories?
I mean, it's a good question. I would say there's a very much winner takes all race on at the moment too in the hardware space. We really don't know whether it's going to be superconducting circuits, topological quantum computers, photons, trapped ions. Like these things are neck and neck. And so, I mean, if you're ambitious and you have like a winner takes all mentality, then you would start a hardware company. And people have done this. Like there are startups that have huge valuations that are trying to build hardware, because it's kind of like, I think about the USB as an analogy. You can imagine that there's all these different ways you could connect memory to a regular computer, and then like something gets momentum and suddenly everything is the same. And I think that will what will happen with quantum computers. Like something will emerge as being clearly the best, and then like that will take over. And then theory is also, so I think you could say that, but you need incredible amount of resources for that to build quantum computers. If you kind of have less money, but maybe you have more people, more computer scientists, then it makes sense to start thinking about whether you can solve these. I would say that the first thing to look at would be to look for these quantum mechanical type problems, ground state estimation, thermal state estimation. Where do they occur in material science, in drug development? And try come up with good quantum algorithms for those that improve the ones that we do at the moment. And that is also another approach that a lot of sort of quantum software companies are taking at the moment.
I think we have a question from an online participant. Please, you're welcome to ask the question. Please go ahead.
Hello, good evening.
Good afternoon.
Yes, the talk was very amazing. So my question is about the quantum inspired approach. I realized that you talk about full tolerance and the NITheCS. What about the quantum inspired approach, which is also a hot topic in quantum computing?
Yeah, so it's another great question. So we know that quantum computers are these like totally different types of computers, and that sometimes we can come up with algorithms that exploit the quantum Fourier transform over groups to solve problems that you can't do with regular computers. But if you're a classical computer scientist, what you might say is like, well, maybe there's a very clever way that I can use a classical computer to simulate what the quantum computer is doing. And that's what people call quantum inspired classical algorithms. So you say, okay, like quantum computing gave these people the kind of conceptual framework and freedom to come up with these new types of algorithms. But maybe for that specific quantum algorithm they came up with, you don't actually need a quantum computer. Maybe there's a clever way that I can get my classical computer to do that. That's called a classical inspired or a quantum inspired classical algorithm. And I think that, yeah, there are many interesting examples of such algorithms. I think it's very important people work on those algorithms, because when you can come up with good classical but quantum inspired algorithms, then you know there's no point in using the quantum computer. But unfortunately, I mean, well, fortunately, I guess, depending on your perspective, I really do believe that there's problems that are just like classical computers cannot do it. And so even if you tried, like, be inspired by the best quantum algorithms, you still won't be able to recreate them. Yeah.
Okay, if there are no more urgent questions, Ryan, thank you very much again for the excellent talk. And